A groundbreaking report has suggested that our current understanding of the universe's age might be incorrect, proposing that the universe could be twice as old as previously determined, with an estimated age of 26.7 billion years. This revelation comes from analyzing data collected during the James Webb Space Telescope's first year of observations, where its powerful infrared capabilities were used to study the early universe. Webb's discovery of high redshift galaxies larger than anticipated has challenged our existing cosmological models, prompting space scientists to reconsider theories about the universe's development, including the Big Bang. But what is the ancient idea that could explain the surprising galaxies observed at the edge of time? And what evidence supports this new proposed age for the universe? If the universe is indeed 26.7 billion years old, how would that reshape our understanding of the cosmos? To understand this breakthrough, we must revisit the 1920s, when a pivotal idea reshaped cosmology. In the early years of that decade, the prevailing belief was that the universe was static, neither expanding nor contracting. However, American astronomer Edwin Hubble's observations shattered this concept. He discovered that galaxies in deep space were moving away from us, with a clear pattern. The farther a galaxy was, the faster it was receding. This relationship between recession speed, v, and distance, d, gave rise to one of the most important constants in cosmology, the Hubble constant. This constant described the rate at which the universe is expanding. By assuming a consistent expansion rate from the beginning, scientists could trace the universe's history back to a point when all matter and radiation were concentrated in a tiny region, marking the beginning of the universe, also known as the Big Bang. This rapid expansion is described by the Hubble time, which corresponds to the age of the universe. Hubble's discoveries also revealed the redshift phenomenon, where light from distant galaxies stretches as the universe expands, shifting toward the red end of the spectrum. The farther a galaxy, the greater the redshift. But not everyone agreed with the expanding universe theory. Fritz Zwicky, a brilliant Swiss astronomer, proposed an alternative explanation, the tired light theory. According to Zwicky, photons of light lose energy through collisions with particles on their way to us, causing a redshift. This theory didn't require an expanding universe or a Big Bang. However, as more evidence supporting the Big Bang theory accumulated, especially the discovery of cosmic microwave background, CMB, radiation in the 1960s, the tired light theory faded into obscurity. Today, the lambda cold dark matter, LCDM model is the standard cosmological model. It describes the universe as an accelerating expanding system, incorporating dark energy and dark matter, and it aligns with the Big Bang theory and the redshift phenomenon. However, recent findings from the James Webb Space Telescope have raised questions about the LCDM model. By examining the distant universe, Webb observed high redshift galaxies that challenge our understanding of galaxy formation and the early universe. The LCDM model predicts that stars should begin forming in the young universe when it's around 150 million years old, with galaxies taking another billion years to form into large, bright structures. However, Webb's observations show large, bright galaxies at redshifts of 11 and 15, only 300 to 500 million years after the Big Bang. These findings conflict with the LCDM model, which would suggest that such massive galaxies shouldn't have formed so early. This discrepancy is known as the G-incomprehensible early galaxy problem. Some astronomers are questioning the validity of the Big Bang theory or exploring the possibility of missing connections in star and galaxy formation. While there is observational evidence supporting current theories, no one is sure why the science is deviating from expectations. The simplest explanation, however, could be a miscalculation of the universe's age, which brings us back to Fritz Zwicky's long-forgotten idea. In astronomy, the concept of angular size and precise measurement is crucial. If we know the physical size of an object, we can calculate its distance. As the distance to an object increases, its angular size appears smaller, but this rule breaks down at extreme distances. As we observe galaxies at greater distances, their angular size decreases until a certain redshift, beyond which their angular size begins to increase. The current LCDM model predicts this shift should happen at a redshift of around 1.5, but Webb observed this shift occurring at redshifts greater than 10. This discrepancy, along with the early galaxy problem, has led theoretical physicist Render Gupta from the University of Ottawa to propose a novel solution. While Zwicky's tired light theory alone cannot explain Webb's findings, Gupta suggests new theoretical approaches to address these challenges. In addition to the drained light hypothesis, the concept of the conveying coupling constant, CCC model is introduced. According to this model, fundamental constants such as the speed of light, Planck's constant, and the gravitational constant are not fixed over time but instead fluctuate, influencing the universe's evolution across an extended timeline. By integrating the CCC model with the drained light hypothesis, Gupta's work offers a fresh perspective on the challenges posed by early universe observations. This approach contrasts with the lambda cold dark matter (LCDM) model, which describes the accelerating expansion of the universe through a constant lambda. Instead, the CCC model introduces a new constant to account for the dynamic evolution of fundamental constants over time. To evaluate which model best fits observational data, Gupta explored several possibilities, including the drained light model alone, the combination of drained light with the CCC model, the combination of drained light with the LCDM model, and alternative versions of the drained light model. Among these, the CCC plus drained light and LCDM plus drained light combinations are of particular importance. The key comparison is presented in a graph that shows the relationship between redshift and the apparent size of galaxies. The blue points represent galaxies observed before the James Webb Space Telescope, JWST data, while the red points represent galaxies observed by JWST. The curves indicate how the apparent size of galaxies changes according to different models. The accepted LCDM model, shown in green, exhibits a turnover at a redshift of about 1.5, diverging significantly from the redshift of the observed galaxies. In contrast, the CCC plus drained light model, represented by the dark blue line, continues to match both the pre-JWST observations and the high redshift galaxies observed by JWST beyond a redshift of 10. Additionally, the CCC plus drained light model predicts that the size of objects at higher redshifts would be 15 to 25 times larger than predicted by the LCDM plus drained light model. This discrepancy in object size provides a potential explanation for the observed prominence of high redshift galaxies, further supporting the viability of the CCC plus drained light model in addressing the challenges posed by early universe observations. According to the CCC plus drained light model, the universe would be approximately 5.8 billion years old at a redshift of 10 and around 3.5 billion years old at a redshift of 20. This extended time frame allows for greater opportunities for galaxies to form and evolve into larger, more luminous structures. The nature of an expanding universe has long been a subject of intense interest and debate in cosmology, challenging our understanding of time, space, and the fundamental constants governing physical laws. As we continue to probe the mysteries of the universe, new observations and theoretical frameworks are reshaping our comprehension. One cornerstone of modern cosmology is the LCDM model, which explains the accelerated expansion of the universe due to dark energy and the gravitational effects of dark matter. This model successfully accounts for various phenomena, including the cosmic microwave background, CMB, radiation, and the large-scale distribution of galaxies. However, recent discoveries from the JWST have raised significant challenges to the LCDM model. By delving deeper into the universe than ever before, the JWST has revealed a population of early galaxies that appear unexpectedly large and luminous at extremely high redshifts. These findings have raised crucial questions about the timeline of galaxy formation and evolution. Specifically, galaxies observed at redshifts of 10 and beyond defy the predictions of the LCDM model, which suggests that significant star formation should not have occurred until the universe was around 150 million years old. Yet, these galaxies seem to have formed complex structures much earlier, within 300 to 500 million years after the Big Bang, presenting the impossible early galaxy problem. This challenge forces us to reconsider our understanding of the early universe's dynamics, indicating that either our current models are incomplete or there are fundamental aspects of physics and cosmology that we have yet to fully grasp. In response to these challenges, alternative theories and models have been proposed to reconcile the observations with existing cosmological frameworks. One such approach is the tired light hypothesis, which was reintroduced by theoretical physicist Render Gupta in conjunction with the CCC model. The tired light hypothesis posits that the redshift observed in light from distant galaxies may be due to the gradual loss of energy as light interacts with particles during its journey through space. Although initially dismissed in the context of the expanding universe theory, more recent observations have prompted a re-evaluation of this concept. Gupta's CCC model takes this idea further by suggesting that fundamental constants like the speed of light and Planck's constant may not be fixed but could vary over time, affecting the observable properties of light and other cosmic phenomena. This alternative framework provides a new way to interpret the observed high redshift galaxies, proposing that variations in fundamental constants could extend the timeline for the universe's development and evolution, potentially resolving the discrepancies observed in the LCDM model. Furthermore, the CCC model's predictions align more closely with the observed size-redshift relationship seen by JWST. Unlike the LCDM model, which predicts a turnover in angular size at lower redshifts, the CCC model continues to predict a reduction in angular size at higher redshifts, in agreement with the observations of early galaxies. These insights underscore the evolving nature of cosmological models and the importance of incorporating new observations into theoretical frameworks. As advancements like the JWST continue to push the boundaries of galactic discovery, they provide critical data that challenge existing paradigms and inspire new avenues of exploration. Each revelation brings us closer to a deeper understanding of the universe's origins and evolution, whether through refining current models or embracing alternative hypotheses. Cosmologists are now positioned to explore new frontiers and uncover the profound insights that lie beyond our current understanding.